All right, I want to continue talking about forces that charges exert on other charges when we have cases of three charges. And in class, we actually did the more complicated example before break. I'm going to take a step back and do a simpler one where all of the charges are in a line. And I think this will help reinforce the other concept, and it'll be a good review as well. So I'm going to draw two charges here and a single charge in the center, and I'm going to give these charges a value and a distance. I'll say, okay, let's see, these are 10 centimeters apart there, and 10 centimeters apart there. You give these charges a size. I'll call that one plus 2 microcoulombs. I'll call this one plus 2 microcoulombs. And they don't necessarily have to be the same size, the two end ones. They could be. Makes things a little bit more straightforward, but they don't have to be. And the middle one I'll make minus 3 microcoulombs. And what I'm going to ask you here is, what is the force on the central charge as a result of the other two charges acting on it? So this charge here, the minus 3 microcoulomb charge, is going to experience two forces, one caused by this charge and the other caused by that charge. So I'm going to want to determine them individually and add their effects to get the total effect that the central charge is going to experience. So I'll just arbitrarily say that F1 is the force caused by that charge, and F2 is the force caused by that charge. And I need to determine the strength of F1 and F2 and the direction of F1 and F2. And the direction is actually relatively straightforward. I could do that right now. I know that the central charge is going to be attracted to the leftmost charge, so it's going to experience a force to the left. And of course, this charge will experience a force to the right, but I don't care. This charge here will experience a force to the right, but that's not what I'm interested in. So I'm only interested in the force that the central charge experiences, in this case, as a result of its attraction to the other charge here, the plus 2 microcoulomb charge. Okay, so I'm going to apply Coulomb's law. And so I'll say, okay, F1, the size of the force 1, those two vertical lines there represent the magnitude or the size of force F1. It's equal to K times Q1 times Q2 divided by R squared, where R is the separation between the two charges. In this case, that's 10 centimeters. And Q1, these should be absolute values also. They're plus 2 microcoulombs for Q1 and minus 3 microcoulombs for Q2, so 2 and 3 times 10 to the minus 6th. So if I do the work here, I have 9 times 10 to the 9th times 2 times 10 to the minus 6th times 3 times 10 to the minus 6th divided by, I have to be a little careful here, I want to make sure these are meters. So I'm going to make my 10 centimeters be what it is in meters, 0.1 meters, which I'll square. Solving for this, on top I have 9 times 2 times 3 times 10 to the 9th times 10 to the minus 6th times 10 to the minus 6th divided by 0.01. Do the math. 9 times 2 is 18, times 3 is 54, times, then I have 10 to the minus 3, divided by 0.01. And this, when it comes up, is going to multiply the whole thing by 100. So I have 54 times 10 to the minus 1 newtons, which is equal to 5.4 newtons. That's F1. Okay, and the direction of F1 is, we already said it's an attractive force, so the minus 3 microcoulombs is going to be attracted to the plus 2 microcoulombs, so it's going to have a sign of negative I hat. So I could say F1, the actual force F1, is equal to negative 5.4 newtons I hat. Okay, that's the first part of the problem. Now I want to do the same thing for F2. F2 again is the force that this charge experiences as a result of attraction to that charge. And it is going to be an attractive force. And that means it's going to experience a force to the right. I could go through the same thing, and I will. I could say, okay, F2, the size of it is equal to, of course, K, Q1, Q2 over R squared. Put the right absolute value signs in there. And again, I have 9 times 10 to the 9th times 2 times 10 to the minus 6th times 3 times 10 to the minus 6th. And of course, this is going to be the same thing I just calculated, 5.4 newtons. But its direction, unlike the direction of the other case, it's going to be I hat, because I know it's an attractive force. So F2 is 5.4 newtons I hat. All right? Now the net force that acts on the central charge is equal to the sum of F1 and F2. And so if I look at this, I could say, okay, F1 is minus 5.4 newtons I hat, and F2 is 5.4 newtons I hat. Add the two together, I get 0 newtons in this case for the net force. And of course the direction is irrelevant here because the two cancel out. All right, it doesn't always necessarily work out that they cancel out, but they do in this case. But this is an example of how you can determine the force on one charge from two other charges. And of course, you could do it with as many other charges as you need or want. But this is the basic idea. Okay, enough for this example.